We have been, in the last few weeks, we've been talking, particularly last week, we talked about a couple of concepts that I just want to revisit, and I'm going to go on from there and expand on that. But we talked about routing protocols, we talked about routing policies, and we looked at firewall filters. Okay, so I think we're all relatively familiar with routing protocols. What about routing policies? What is the purpose of a routing policy? Anybody tell me? What are we trying to achieve with a routing policy? So if we think of a routing policy, what is the central focus of a routing policy? What would be, I guess, the entity that is the focus of our policy? Any ideas? It's actually the routing table. Okay, so the focus of a routing policy is the routing table, and the purpose of a routing policy is to control what is either imported into our routing table or exported out of our routing table. So what we're talking about is route advertisements being received and then evaluated and either imported into our routing table unchanged or imported into our routing table and modified as we do the import, or not imported at all into our routing table. And also with regards to how we re-advertise routes out of our routing table. So we can decide that we're going to re-advertise certain routes from our routing table. We can modify the routes as they're advertised. We can modify some of the attributes of those routes as they're advertised out. So it gives us control over routing information that is received or re-advertised to other routers. So why would we be interested in that? Why would we want to do that? Because if we control the routing information that we receive and send, then that routing information will control the flow of traffic on our network. So our ultimate goal is to control the traffic. What happens to the traffic on our network? And so by controlling the information that we actually are sending out, the routing information that is being sent and received, we can ultimately control the flow of traffic. So let's just continue that thought. And we did talk about firewall filters also last week, which is what can we say a firewall filter is? Have we seen anything like that before? Anywhere? Have we seen anything like a firewall filter before? Does it look a bit like an access control list in our Cisco course? Yeah, it does the same thing. Okay, it does exactly the same thing as an access control list. We just go about it, building it a little differently. Okay, so the point, one of the points of what we're learning here is that these things that we're learning are not unique to Juniper devices. Okay? These things that we're learning are standard operations on all networking devices. It doesn't matter. Cisco have the same functions on their devices as Juniper does. So does HP on their devices, for example. So the point is that you're pretty much going to want to do similar things regardless of what the actual manufacturer is. It's just how you go about doing it. Okay, so the point of learning multiple platforms is to get you out of being, get you out of a mindset that says I can only use this particular type of device or this particular manufacturer of device, or I'm limited to a particular brand of device. What we want to do is to break you out of that and realize that in reality, all the devices have the same goals. They perform the same functions, or pretty much very similar functions, and it's just a matter of how do you make that device do what you need it to do. That's ultimately what we're about. Of course, different devices do have different features, and you know, there are specific features that you may look for in a particular device. But ultimately, the point is that different manufacturers often make these devices that have the features you're looking for, and you should not be limited to a particular brand. That's the point. All right, so we're going to continue that discussion, and we're going to be looking at some other things here we want to get into. We want to get into the typical uses of static, aggregate, and generated routes. So a little bit of terminology there right off the bat. So obviously we know what static routes are. What's an aggregate route? Have we heard of anything like that before? An aggregate route? Well, another name for an aggregate route would be a summary route. Have you heard of a summary route before? What is a summary route? Well, we have talked about it, but we'll get into it again. And we're going to talk about this thing called a generated route, which is really akin to an aggregate route. So we're going to get into configuring and monitoring static, aggregate, and generated routes. We're going to look at the purpose of Martian routes. And we're going to add some new entries to the list of Martian addresses. And describe typical uses of routing instances and configure and share routes between routing instances. So we haven't really got too much into routing instances. We have sort of talked about it a little bit. We haven't really got into it very much, so we're going to get into that a little more. So let's get into static routes. First up, start with the easy one. Okay. So here we are, manually defined routes added to the route table. So default route is an example of a static route. And here's an example of a route configured. How do we, let's just issue the show route command. And we've got an IP address there. So what we're asking the router is show me what routes you have to this particular IP address. And we've got our result here is that, well, we've got a static route. Okay, so we're going to use our static route to get to that particular address. Does that make sense? We also see that we're going out of interface GE001. Okay. So where do we define static routes? They define under the Edit Routing Options hierarchy. And when we configure them, they will consist of a destination prefix, which is the network we're routing to, and the next hop. So it's nothing unusual. This is standard stuff that we're used to. We're going to say what network we're routing to and the next hop. So what is the next hop? Well, it's the IP address of a directly connected device. We can look at other options, and we will look at why we would want to use these other options as discard and reject as a next hop. We'll actually show you that as to why we want to do that. We've also looked at the qualified next hop parameter as well, and we looked at what that does. So what we discovered is that if we have a qualified next hop, we can set a different preference. So in other words, we can have two next hops, for example, for a particular route. And we can have a different preference on the qualified next hop than the other next hop. And why would we want to do that? Any ideas? What does setting a different preference do? If I've got two next hops to the same network, but they have a different preference, what is the effect of doing that? Anybody? What does preference do? It makes the router choose based on the preference, and what's the deciding factor? The number, okay. And is the biggest number or the smallest number more preferred? The smallest, yes. So the lowest number wins. All right. So what's the? We did something very similar to this. In fact, exactly the same as this in our CCNA course, but it wasn't called route preference. It was called something else. What was it called? There was a setting, a number that did exactly the same thing. It's called administrative distance. All right. So it really administrative distance is really a route preference. Okay, and it's a preference based on the source of the routing information. Okay, that's really how it works. So here we have a situation where we can have two next hops to the same address, and I can give one of them a different preference to the other. Why would I want to do that? Why? Why would I want to do that? What difference, what effect does that have? Well, the most preferred next hop would become the active route. That would be the one that goes into the forwarding table. So we would be forwarding traffic to the most preferred next hop. That's where we're forwarding traffic to. What does the other one do? Nothing. Until we lose the first one. Okay, then the second one goes active, and that goes into the forwarding table, and then we send traffic to that one. Is there a situation where I might want to do that? Can you think of one? Okay, what about I have got two internet connections. One is a 4G connection. The other is a high-speed fiber connection. All right. Which one would I want to use on a normal everyday basis? My high-speed fiber connection. Exactly. So how could I do that? Well, I would have a default route, which would be my route to the internet. I would give one of them a qualified next hop. And the effect of that would be one of them would be more preferred than the other. So I'd make sure that my high-speed fiber connection was more preferred than my 4G connection. Okay, so in normal operation, everything's working nicely. I am forwarding traffic to the internet out of my high-speed fiber connection. But what happens if there's a huge explosion at that particular ISP? I don't know, everything burns to the ground, no more connection. Yikes. Guess what? Instantly, okay, even if it's not that catastrophic, they have a power failure, okay, it goes out for an hour. All right. Instantly, my router says, hey, I've lost connectivity to that next hop. I'm going to drop that route out of my routing table. I'm going to install my other next hop into my routing table, and traffic, I still have an internet connection out through my 4G. Okay, power comes back on at my ISP, everything's happy, they get their generators going, whatever it is, and my other next hop becomes available, boom, boom, it comes live again. So my cable, my high-speed fiber will become the live next hop. Okay, so it is a backup, all right? All right, so that's how it works. So, little note down the bottom of the slide here, routes with an invalid or unreachable next hop will not become active. All right, so if the next hop becomes unreachable, then that route will drop, it won't be in the forwarding table, it will drop right out of the forwarding table. So we won't be sending traffic there. All right. little note here that we have to use the resolve command if the next hop is not directly connected. And there may be times when you want to do that. It's not a usual way of doing it, by the way. That would be unusual. Okay, so here's an example here. Under edit routing options, we've got a route. We've got a default. This is an IPv6 route, and we're actually setting a route preference right there. You can set a route preference on any next hop. You don't have to use the qualified next hop statement to set a route preference. You only do that when you've got 2 next hops, or more than 1 at least. But you can set a route preference on any static route. You can also go over into the static defaults section and change the default preference. So by default, the preference of a static route on a Juniper device is 5. That's the default preference, route preference of 5. So we can go and change that. You can change your defaults if there was some reason for doing it. It wouldn't be something you just do, but if there was some reason for doing it, you could. So we could change our preference. Just to say we did, let's just say we changed our preference to 250, and let's just say we had we've got a default route here. We've got 2 next hops, 1 to 172.30.25.1, and we've got another next hop to 172.30.25.5, and it's a qualified next hop, and we've got a preference of 251. Incidentally, just looking at that there, with that default, which one of those next hops will become active? Is it the 25.1 or the 25.5? Which one's going active? Yes, the 1, because it's got a preference of 250, which is lower than 251. Okay, so let's look at this other route here. We've got a route to 172.28.102.0/24. Next hop is 10.210.11.190. We've got the no re-advertise parameter on there. What's that do? You know what that does? No re-advertise. Okay, what that means is that if just say we have a routing policy, and the routing policy says from protocol static, then accept, and we apply that routing policy, say, to our OSPF protocol as an export policy, and the result is we're exporting all of our static routes into OSPF, so it will re-advertise them. Well, if I had that particular routing policy, then I would, what the policy does is, if it's a static route, then we're going to be accepting it as part of this policy, and if I export it, then what that tells me is I'm going to be exporting all my static routes into OSPF. However, by having this no re-advertise statement on this particular static route, it prevents it from being re-advertised or exported into another protocol. Okay, now what we're saying is, well, we don't ever want this route to be advertised by another protocol. And one of the reasons that might be is that maybe that is a route that gets a route back to our management network. So really, that route is not, the purpose of that route is not for forwarding traffic, it's not for forwarding transit traffic through our router. It's really just there so that we can connect to it and manage the device. Okay, so basically that route, for example, would be, if we're going to have an SSH connection into our device needs to know how to get the return traffic from that device back to us. All right, back to the network that we're in. Let's just say we have a VPN connection into our device. All right. Well, if we're going to be connecting via a VPN, our device needs to know how to get the traffic from it back to us. All right, and we would have to put a route in to do that. In actual fact, when you guys connect, right, to your devices remotely via VPN, your device does have a route that tells it how to get the traffic back to you, right? Because that route has been put in or added to the standard Juniper Lab configs. So we've actually modified all the Juniper Lab configs and added an extra route. And if you look at it, you'll see that it actually has the no re-advertise parameter on it, okay, because that's the purpose of that route. Little note here, highly suggested for static routes used for management traffic. All right. Everybody understanding that, what we mean by that, management traffic, and why we would need a route to actually allow us to connect to a device remotely? All right, because the device needs to know, okay, I've got a route to the device, but basically the device needs to know how to get return traffic back to me from wherever I am. So it needs a route to get that traffic back. Otherwise, I can never log into it and establish a connection from the management network. Alrighty. So here's another example. Which next hop will be used in this example? So we've got to set our default preference for static routes to 180, and here we have a default route. So we've got two next hops, one to 25.1, one to 25.5. Which of those is going to go active? Just looking at that example, is it the .1 or the .5? It is, in fact, the .5, yeah, because we've got a lower preference number. The default has been changed to 180. All right, let's look at this example here. Which of these static routes will be exported into OSPF? So where's our policy? Here it is here. Here's our policy statement, which is the policy is called export to OSPF. We have a term which says match static routes. Here we go, from protocol static. And then we've got this route filter here where we're looking at static routes for a particular network. So basically it's anything starting with 172.29 will match that. So we're looking for any static routes to networks beginning with 172.29. We're going to accept that. And we have got, in our routing options over here, we've got a route to, well, looks like we do have a route to 172.29.12, 172.29.13. So we've got two routes over there. One of them's got the re-advertised parameter on it. You will notice we've also got some other routes to 29.16, 29.20. So we've got four routes advertised there. We've got 29.12, 13, 16, and 20. And we've got an export policy on OSPF. So we're looking at what we're doing is we're taking all the static routes that are to networks beginning with 172.29, and we see we have four of those routes, and we're going to export them into OSPF. Okay, so the question is, looking at that routing policy, looking at those routes that we have, looking at the fact that it's applied as an export policy to OSPF, which routes are exported? And the clue is, of course, the no re-advertise parameter on one of them. So first of all, what matches the route filter? Any of those static routes to network beginning with 172.29? Yeah, they all are. All right, so there we are. We have four static routes that match the policy. Okay, then accept. So they are. So they all match the policy, and now we're going to apply that to OSPF. So what we should be doing now is pulling all those four static routes out of our routing table and exporting them into OSPF. Happy days. Except one of them has got no re-advertise on it. All right, so actually, in fact, there's only three that are going to be re-advertised. It's 12, 16, and 20. Okay. that make sense? Okay, so what are we saying? If you have a route that you do not want to be re-advertised because it's not for transit traffic or for any other reason, just put the no re-advertise parameter on it and it won't be re-advertised. Okay, that was static routes. Okay, we looked at static routes, route preferences, things we can change, things we can do there. Okay, any questions before we move on? Are we all good? Are we okay? All right. A lot of silence in this room. It's like, I know we're just stunned, you know, like, okay. Alrighty. So let's look at aggregate routes. So what is the purpose, by the way? What is the purpose of an aggregate route? Why do they exist? They exist to make routing more efficient, right? To make routing more efficient. The reason that we use these routes is to reduce the size of our routing table, so that we can have a whole collection of network destinations represented by a single route. Okay, a single route. So, I mean, let's just, I mean, the ultimate, I suppose the ultimate aggregate route is the default route, isn't it? Because it represents absolutely everything. Okay, so, but let's take a look at some other aggregate routes here. So, typically used to reduce the number of route advertisements. So, instead of us advertising network A, B, and C separately, we advertise one route that represents all of those networks. That route is an aggregate route, also known as a summary route. It means the same thing. When we did our CCNA course, they were called summary routes. Juniper called them aggregate routes. They're the same thing. You will find that this is not an unusual situation to find different vendors using a slightly different name for the same thing as another vendor. Okay, so one example of that is if I'm configuring a Cisco switch and I want to send tag frames on that switch from out of a port, Cisco say that's a trunk port. If I'm doing it on a HP switch, they just call it a tag port. They don't. The word trunk does not appear anywhere. So I'm thinking, I want to set up a trunk. I want to set up a trunk. How do I set up a trunk? I can't see anywhere where I can set up a trunk. No, you never will. They don't call it a trunk. They call it tagged. Okay. So what you have to think is, yes, the frames are tagged to go out there. I want the tags to stay on. Okay. So you kind of understand what's happening here to make sense out of something. So that's just another example. So different vendors do call different names for exactly the same thing, but this one's not so hard. Is it aggregate? Summary kind of does mean the same thing. All right, so it's a manually defined route that represents a collection of more specific routes typically used to reduce the number of route advertisements. And, okay, here's one for you. Oh, the answer's already there. It's too easy. Can't go back. No, sorry, I can't take it off. Oh, gee. Which of these prefixes are part? I'm just put my hand over that. Which of these prefixes? Which of these prefixes? Too late. Which of these prefixes are part of the 10.1.0.0/20 aggregate route? What do I have to think about here? I have to think about what is captured by that 10.1.0.0/20. Okay. Well, the first thing you think about is, okay, a /20 is a block size of 16 in the third octet. That's the first thing. So starting at 0 then. So what does that block of 16 encompasses? Well, it encompasses everything between 0 and 15. Okay, so that's why the 10.1.14 and the 10.1.15 are included in the route and the other ones are not. Okay, so again, block size is the way to begin to think about these things, okay? Where's the block? All right, so configuring aggregate routes. Let's have a look. It's under the Edit Routing Options hierarchy, and let's do a show here. We're going to do a show route protocol aggregate, and here we have a aggregate route. What's it saying? It is 172.29.0.0/22. What's the block size of that, by the way? What's the block size of that? /22. It's in the third octet, block size of 4 in the third octet. Okay, so what would it encompass? 0, 1, 2, and 3. In our diagram, we don't happen to have a 3. That's okay. It's still going to work. Okay, it's still going to work. It encompasses the networks that we want to, includes the networks we're interested in. All right, no problem. So it's an aggregate. I just want to notice that the preference of an aggregate is 130, and the next hop is reject. Oh, hang on, what's going on there? Why is the next hop reject? We'll get into that and find out why it's reject. Okay, so for an aggregate route to go active, it must have at least one contributing route. What is a contributing route? Any ideas? Okay, let's just get our head around what's happening in this R1 router. What's happening in R1? Okay, R1 is advertising this aggregate route. It's advertising it out to all those whatever downstream routers there may be. So it's advertising. So this arrow here is the direction of routing information, not network traffic. Okay, it's the direction of routing information. It's flowing from R1 over to ISPX. However, R1 is also receiving routing advertisements. It's receiving 3, at least. It's receiving an advertisement from network A, network B, and network C. Okay, now, because we're looking at an internet type scenario here with an ISP, etc., ignore the fact that we're using private address ranges here. Okay, just ignore that fact. In reality, we're probably talking about BGP routes here, and we're probably, in reality, if this was a real scenario, we would actually be advertising public IP addresses out here in a real world scenario. So what's happening is it's probably R1 is probably receiving 3 BGP routes, and it's advertising an aggregate route out. Okay, so the contributing routes are the 3 routes that it's receiving from network A, B, and C. So it has contributing routes. Now, the point of this is that ISPX is going to get this aggregate route. What ISPX is essentially going to get is a route that says the network is 172.29.0.0/22, and the next hop is 172.30.25.2. Okay, which is interface GE001 on R1. So ISPX says if I've got any traffic that's headed for 172.29.0.0/22, I'm going to send it to my next hop, which is R1. Does that make sense? All right. So what it's doing, it's telling ISPX where to send that traffic. Okay, that's fine. That traffic is going to arrive at R1, and R1 is going to have in its routing table those 3 contributing routes, which will tell R1 where to send traffic to each of those specific networks. So R1 has got the more specific routes. That's fine. That's R1's job. What we don't want to do is have to advertise out a whole bunch of routes when we could be advertising just one. Okay, that's the point of this aggregate route. Does that everybody understand the point of that as to what this is doing? Are we okay with this? All right, anybody got any questions? Now is the time to ask. Okay, now is the time. All right. What the effect of this is ISPX will send traffic to R1 for any routes that fall within that aggregate route. R1 has the more specific routes, which are called contributing routes because they fall within the block of the aggregate. Okay, so far so good. All right, all good. Okay, here's a sample aggregate route configuration. We have got edit routing options. We are under aggregate. We've set up some defaults on our aggregate route. This community term here is a BGP attribute. Okay, so immediately I'm knowing, okay, well I'm talking about an ISP situation here, and we're looking at BGP protocols. I have got two aggregate routes here, in fact. 172.29.0.0/22 and 172.25.00/16. I'm putting a community parameter on the second one, and I've got the discard parameter. Discard will silently discard the packet destined for a contributing subnet for which a more specific route does not exist. We'll kind of get into that in a little bit more detail. All right. So let's take a look at the route here. So we have got show route 172.29.00/22, which is our aggregate. I'm going to use the exact and the detailed parameters because I want to get all the information about this particular aggregate route. We're on R1 here, so this is R1. So next hop is reject. Don't panic. We're not going to reject the traffic. Okay, don't panic. We're not going to reject it as long as we have these contributing routes active. Okay, so as long as we've got at least one of these routes active, we won't be rejecting the traffic. Okay, if we lose all of these routes, all those contributing routes, then we'll be rejecting traffic to that aggregate. Okay, so we have an aggregate route. This AS pass stuff, that's all BGP stuff. We haven't covered BGP yet, so that's kind of like voodoo to you guys right now. It's like, what is that? Okay, so we haven't covered BGP. Don't panic. We will. What we do have down here is contributing routes. In actual fact, these are direct routes on directly connected interfaces, as it happens here. So we've got these three contributing routes right there. Okay, so that's a look at our aggregate route. So we are advertising out 172.29.00/22, but we also have in our routing table the contributing routes to that aggregate. Okay, they all fall within that block. Are we good? Everyone good with that? Okay. So what action does R1 take when it receives a packet? When it receives packet A and packet B? Assume the default next hop behavior. Okay, so packet A arrived at R1. The destination IP is 172.29.1.5. What happens? It goes to network. Where's it going? B. All right. 172.29.1.0/24. That's network B. So it belongs to network B. Okay. What happens is if it receives 172.29.3.5? Any ideas? It doesn't have a route to that. It doesn't have a route. So it's going to drop it, and it'll send a message back to ISPX. All right. So that's an aggregate route. Okay. So just in a basic concept, okay, the point of it is to collect a bunch of routes into one route and advertise that one route instead of having to advertise all the networks individually. We advertise them in one block. This is common practice, particularly on the internet, where we have thousands of networks. Imagine if a router had to have thousands of networks in its routing table, but the internet would grind to a halt because of just the time it takes to do all the lookups. Okay, it would just grind to a halt. So that's not how it works. So essentially, on the internet, we just use aggregate routes, which represent massive blocks of networks, and which is again why IANA delegates blocks of networks to regional registries, right? So basically, all of America, for example, has a block of addresses. So I can have an aggregate route that represented that entire block of addresses for any traffic that happened to be going to America. And same goes for Africa, and there's other, other blocks as well. We've got Asia here where we are. So in the Asia region. So that's the point of aggregate routes. Okay. Right. So what is a generated route? Well, basically, a generated route is a type. You could say it's a type of aggregate route. All right, but it's not statically configured. It is created by policy. All right, so what an aggregate route is, we say, if these conditions exist, then create this route, or then route the traffic here. Create this particular route. So difference is the use of a forwarding next hop, which is the next hop associated with the primary contributing route. So there is a thing called a primary contributing route. Can be used to generate a route of last resort, often default route when required conditions are met. So what we're doing is here, we're evaluating conditions using a policy, and if conditions exist, we then create this particular route. If conditions change, then we don't create that particular route. So it's useful when you don't necessarily want a static route that's there all the time, but if certain conditions exist, then you want to send traffic to a particular next hop. So let's have a look at this one. We've got a Tier 1 ISP, 10.000/16. Core prefixes sent from Tier 1 to a regional ISP. Default route is sent from the regional ISP to customer X if core prefixes are active in R1's table. Okay, so what the regional ISP is saying here is that if I have got connectivity to my Tier 1, then I'm going to advertise a default route to customer X. So I'm going to say to customer X, send all your internet traffic to me because I have got an active connection to my upstream Tier 1. But if I lose my upstream connection to my connection to my upstream Tier 1, then I'm not going to tell customer X to send all the traffic over to me because I basically don't have a connection to my upstream Tier 1, so I wouldn't be able to forward that traffic anyway. That traffic would be dropped. Okay, so if this was a static route, if this was like a summary route that was re-advertised, or even a static route that was just in place, that traffic would keep going up there, and it would basically go nowhere. You'd basically lose, really. You wouldn't be able to send traffic to the internet, okay, because it would all arrive in the regional ISP, and the regional ISP would drop all that traffic because it would not have an active route to its upstream Tier 1. So what we're saying here, and in this scenario, we can also assume that customer X is running, say, probably BGP as its protocol. Okay, that would probably be what's happening there. So we could also assume that probably customer X has got more than one ISP, even though it's not on the diagram. Just looking at the situation and the conditions of that scenario, we'd probably assume that customer X had more than one ISP, so that if its regional ISP lost connectivity to its upstream tier 1, it would stop advertising a default route down to customer X, so customer X would no longer have that route in its routing table, and presumably it would have some other way of getting traffic out to the internet. So I mean, that's not in the diagram, but if you're looking at that situation, you think, well, why would you do that? And that's probably the reason. Okay, so everybody got the concept here? What's going on? Are we good? Okay, so the concept, what the regional ISP is saying is, if I lose connectivity to my upstream tier 1, I will not tell my customer to route all this traffic to me. Okay, that's what's happening here. This is called a generated route. Okay, so there's a condition. The condition is I'm getting routes. I'm got a route to my upstream tier 1. That's the condition. All right. If that condition is met, then I will generate this default route. So let's have a look at it. We want to configure R1 to generate and advertise the default route into OSPF when the 10.00016 BGP route is present in its routing table, which is kind of a summary of what I just said. So there's R1. All right, sample generated route. We're under the show routing options, generate, default, we've got a preference of 130, we've got a route, which is a default route sitting under my generated routes there. And the parameters defined under defaults are applied to generated routes. So we've got a preference in there. It's all good. And here's our policy configuration, because remember with a generated route, it's always some kind of policy or situation we're evaluating, and this is it here. So under edit policy options, this is a term called match BGP prefix from protocol BGP route filter 10.00016 exact then accept. Term else reject says then reject. So what we're saying is we're filtering on this particular route 10. So what we're saying is our upstream ISP is going to advertise this route to us, 10.0.0.0/16, and this is under edit policy options. We have got a from protocol aggregate route filter, which is our default route, exact then accept. Okay, so looking at our policy options here. And this is where we apply it. So we've got our generated route there, edit routing options, generate, we've got our preference, then we've got our route, which is 0.0.0/0, policy match contributing prefix. Let's go back up to the previous slide. And here's our policy here. The policy statement is called match contributing prefix. So we are referencing the policy right there in our generated route. So a generated route is generated based on a condition, which is evaluated by the policy. So we're evaluating the condition. The condition is, let's go back up again. The condition is, do we have the 10.0.0.0/16 route in our routing table? Have we received that route? And if we have, then we're going to generate this default route, and we're going to put it as an export policy under, in this case, OSPF. In fact, so we're actually going to be advertising that route via OSPF to our customer. by the looks of it. I'd say. So that's the condition. So the thing with a generated route is that it is based on a particular condition existing. If that condition exists, then we will create this particular route which we will advertise. Okay, so that's the point of a generated route. How are we doing for time? All right. And this is the show route exact details. So we're showing our default route, and it comes up as, actually it shows as an aggregate, but we have this contributing route here, which is in fact the policy that we're evaluating here, 10.0.0.0/16 protocol BGP. So that's our contributing route. Alrighty, let's look at monitoring the results again. Let's do the show route 00 exact command. And on R2 or R3, which are the sort of the routers back behind R1 there, and we will see the fact that we have got a default route via OSPF. So OSPF is re-advertising that default route. It's got a preference of 150. Okay, so the result of that is that default route is exported into OSPF. OSPF re-advertises it to the other routers, and there they have a default route. Okay. So if we lost our connection, if we lost this 10.0.0.0/16 route, then that default route would no longer be advertised by OSPF. Okay, because the policy condition would no longer be met. So it's a conditional route. So a generated route is a conditional route. Okay, that's what I'm thinking about it. Okay, Martian addresses, they're just addresses that we are not going to be processing, and really they're mostly private address ranges or address ranges that are reserved for a particular purpose. So that's some of the addresses that are never installed in the routing table. So that's a pretty standard thing for most routers. I don't know what they're called Martian, but they are. There they are. And we can add. And the point of this is we can add extra. We can add extra addresses that say, well, we are never going to route to these addresses. Okay. And as you said, that generally they're private ranges or addresses that are reserved for a particular purpose that we just don't route to. So we can do that. Okay, so not much to say there. Routing instances, we didn't mention routing instances. Can we tell me what a routing instance is? What is a routing instance? Anybody's forgotten it? Okay. All right, so I think what I might do, we're going to get into this and talk about it in a little bit of detail early, and let you have a bit of a break, and then we'll come back and we'll get into routing instances, find out what they all are, what they do, and we'll go from there. So I'll spend a little bit of time on this. So let's take a break, and then we'll get back into it after lunch.